Dear friends, please subscribe yo.com and press the bell button for recent updates. Thank for watching.
Welcome students. In this session we are going to study assembly language programming of 8051 microcontroller, the ALP of 8051 microcontroller. So this is the last topic of unit 4. Okay, so it is very easiest one. Just we are going to refer some programs, how to make a program. Okay, let us enter into video.
U.com.
So first we are going to see the addition program. So addition of two 8-bit numbers. So in the last session we have studied instruction set. So according to that, here we are going to write some program. So to write the program we have to follow the format, that is we must make a table that containing the address, label, mnemonics. Okay, 3 columns: address, label, mnemonics. Address is a starting address of program is entered. Label, here we are considering the label that is useful for loop operation, and the mnemonics is the instructions. Okay, mnemonics is the instructions. 3 columns are available in assembly language program of 8051. So here the addition of two 8-bit number, that is useful to add two 8-bit number and store the result in a memory location. Okay, so initially the first instruction is clear C. So C is a register that is useful to clear, actually the C equal to 00. Then after that move R0 comma 00. So R0 is a general purpose register. Okay, we are moved the data that is 00 to R0. Then move A comma 05. This is the first data. Here we are going to add the 05 and the 03. So the first data that is moved to A register. Similarly, the second data that is a 03, that is also moved to B register. The the 05 and the 03 is in immediate addressing mode because the hash symbol is present, so it is a immediate addressing mode. Then here performing the addition, add A comma B. Now the result A and B are added. The result is stored in accumulator. Okay, so now the addition procedure is over. After that we have to store the result in memory location. In order to store the result in memory location, first we declare the memory location, that is 9200. That is moved to data pointer dptr. Okay, then here we are consider one condition, that is JNC ahead. JNC means jump no carry. So after the addition, here we are checking the carry flag, whether the carry is generated or not. Okay, so if the carry is not generated, here jump to this location, this instruction. If carry is generated, here INC R0. Okay, you do INC R0. So jump no carry, carry is not generated means we have to execute this instruction and skip INC R0. If carry is generated, then we execute INC R0 in continuous manner. Okay, so move if carry is generated, we are incrementing R0. Initially R0 equal to 0, so it is set to 1. Then after that move X dptr comma A. So dptr point the address 9200. So in that location we are moving the accumulator data. So accumulator containing the addition result. Then after that incrementing the dptr. Then after that the R0 value is moved to accumulator. Then that value is moved to dptr second address, that is 9201. So the R0 is used for carry purpose. Okay, that is used for carry. Okay, so the sum is stored in 9200, carry is stored in 9201. So after that yes, jump here. So the program is terminated here. Okay, so this is the addition of 8-bit number. Next one, the subtraction. So subtraction also same program. Addition and subtraction both are same program. Instruction, instead of add a comma b, here we are using subv a comma b. Okay, subtract with borrow. Okay, that is used here. The remaining all the instructions are same as the addition instructions. Okay, right. So here jump no carry means if the borrow is present, we are executing increment or not. Borrow it not present, we are not executing increment or not. Directly I come to this instruction. Okay, so this is a subtraction. Addition and subtraction both are same, only one instruction is different, that is sub a comma b. Okay, next one is a multiplication. So if we are doing the multiplication, we are loading the data in accumulator and B register. So one data must be in accumulator, another one data in B register. Okay, after the multiplication A cross B, so we have a 16-bit result that is stored in A and B. The lower 8-bit is stored in A register, higher 8-bit stored in B register. Okay, see the program. Move A comma 25, move B comma 65. So 25 and 65 both are immediate data. Then we are doing the multiplication. So 25 across 65, the result is E99. Okay, so in this case, 99 is stored in A register, 0E is stored in B register. Okay, so the result is 16-bit number. Actually here 12-bit number. E99 is a 12-bit, but here we are considering around 0 here, so that is become a 16-bit number. So lower 8-bit is stored in A register, higher 8-bit 0 is stored in B register. Okay, this way we can store the multiplication result. So already we have studied this table in instruction set. Okay, right. Next one, the divide operation. Divide A by B means the same concept. Okay, so say one that is a first data that is loaded into A register, second data loaded into B register, then divide AB means now A equal to 09, that is a quotient stored in A register, remainder stored in B register. Okay, so this is a divide operation. So division, numerator is A, denominator is B, so quotient is stored in A register, remainder is stored in B register after the division execution. Okay, next one, the program for multiplication and division. So in multiplication and division, the programs are same, only one instruction is differ. See, first we are going to see the 2 8-bit number multiplication. The first data is loaded into A register, second data loaded into B register. Actually B register is represented in the form of address, if not indicate the B register. Okay, right. So we can use the B also. Okay, but here directly they used the address of B register, that is F naught. Then multiplication MUL AB. Now the result is stored in A register and B register. So now we are moving the result into memory location. So that is a 9200. The 9200 is loaded into data pointer. Data pointer point the 9200. After that we are moving the accumulated data to data pointer. Now the accumulated data is stored in 9200. That is a lower 8-bit is stored in 9200. After that we are incrementing DPTR. Now the data pointer point 9201. Okay, 9201. Now we are moving the B register value into A register, that is a F0 is moved to A register. Okay, after that we are moving the A register content to DPTR. Now the second 16-bit second 8-bit is stored in, higher 8-bit is stored in 9201. Okay, right. So then now after storing the second 8-bit or higher 8-bit, the program is terminated. Okay, so here each address can store 8-bit data only. So lower 8-bit stored in first address and higher 8-bit stored in second address, that is 9201. Okay, how it is incremented? So increment DPTR increase the 9200 to 9201. Okay, this is a multiplication operation. So the same program is used for division also. So only one change is DIVAB. Instead of MULAB, here you are using DIVAB. Remaining everything is same. Okay, right? So this is a division of two 8-bit numbers. Okay, so in multiplication and division, you must know that the result is stored in A register and B register. Similarly, in a microprocessor 8086 microprocessor, the multiplication during the time of multiplication operation, the result is stored in A register and D register. Okay, so in 8086 the multiplication result is stored in A register and D register. In 8051 the multiplication result is stored in A register and B register. Okay, right. Next one, a general program, that is the average of 5 numbers, 8-bit numbers. Okay, so here we are going to find the average of 5 8-bit numbers. Okay, so first we are storing the 5 numbers in memory location. Okay, that is the first number stored in number 40. So move 40h comma immediate data 05, then 41 we are 04, 42 03, 43 02, 44 01. Okay, then 5 data are stored in the memory location from 40 to 44. After that we are moving first data to R0. Okay, moving the first address 40 is moved to R0. So now the R0 points a memory address, the first memory address, that is 40. Okay, right. After that move R5 comma 05. This is R5 is used for counting purpose. Actually totally we are using the 5 numbers of data, so here we are consider the 5 05 is act as a counter. Okay, then after that the R5 value is moved to B register also. Okay, R5 value, that is R5 equal to 05, that is also moved to B register. Okay, so initially we clear the accumulator. Okay, before we are doing the addition, we are clear the accumulator. Then here we are forming one loop. So that is add A at R0. Okay, so R0 is R0 points 40, that is a memory address. At R0 means, so the memory address containing one data that is added with the accumulated data. Initially accumulator equal to 0. So 0 plus 05. Now the accumulated data is 05. After that we are incrementing R0. So now the R0 value is incremented. What is R0? R0 is initially 40. Now it is incremented. Now R0 equal to 41. Now R0 points 04. After that decrement jump no 0 R5 then loop. So decrement the R count. Actually count is R5. Okay, decrement R5. Now R5 equal to initially R5 equal to 05. Now after the decrement R5 equal to 04. Okay, then we are checking the condition. Jump no 0. R5 is whether 0 or not. Okay, it is no 0, so it is R5 is 4, so it is not a 0. Then we are continuing the loop. Okay, now we are doing the same procedure again and again, and every time the R5 value is decreased. When the R5 reaches 0, the loop will break. Okay, after that we are divide AB. So B value is already that is loaded from R5, that is equal to 0 by B equal to 05, that is a total number of data in a array. Okay, so divide after the loop breaks, so we have a result of summation of all the data 0 2 3 4 5. These all the data are added. Then we are divide AB means that the sum divided by total number of data. Okay, that is a 5. So we will get a average. That average is present in accumulator register. Okay, then we are moving the data to accumulated data, that is quotient, that is average, that is moved to 55. 55 is a memory address. So from the 55 we can find the average of the 5 8-bit number. Okay, right. So very simple. Initially we are adding all the data by using the loop. Okay, and the count value. So every addition the count value is decremented by 1. Then every time it will convert, it will check whether the count value is 0 or not. Okay, then if it is the count value is 0, then the loop will break. After that we are making the division. If the count value is not 0, the loop is again continue to add the next data. Okay, so this is the average of 5 8-bit numbers, very easiest way. Okay, next one, checking an input bit. So we have checked the input bit, that is a IO line. So by using the JNP, we can check the input bit JNB and JB. JNB means jump if no bit. JB means jump if bit. No bit means that is 0. JB means equal to 1. Okay, assume that the program, okay, so the problem is, assume that the bit port 2.3, so port 2.3 is an input and represent the condition of an oven. If it goes high, it means that the oven is hot. The monitor the bit continuously. Whenever it goes high, send the high to low pulse to port 1.5 to turn on buzzer. Actually, this is a one small project. So the oven status or the oven temperature is connected with port 2.3. Okay, and buzzer is connected in port 1.5. Whenever the oven temperature is increases to some high value, some level as high, then at the time the buzzer is switched on. Okay, the buzzer is switched on. Whenever the temperature is reduced, at the time the buzzer is switched off. This is a condition. How we can write the program? Okay, so here we are considering one loop, that is a JNP, jump no bit port 2.3. okay, jump no bit means low. Okay, right, so that is low. And here this, actually here jump no bit port 2.3 here. So that means jump no bit means the port 2.3 is low. Okay, that is 0. That means the oven is low temperature. When the oven temperature become high, at the time port 2.2 2.3 receive active high input. At the time this loop will break. Then set B means port 1.5 set to 1. Okay, set to 1. At the time the buzzer will turn on. Okay, buzzer will turn on when set B port 1.5. okay, after that we are after some time we are clear the port 1.5. okay, then the program is terminated. Okay, so automatically buzzer is switched off. Okay, so this way we can check the particular pin by using this loop. Here jump no bit port 2.3 here. Okay, if when will this loop break? Port 2.3 became logic 1. At the time the loop will break. When the loop will break, set B, next instruction set B 1.5 is executed. Okay, if it is executed means that produce some pulses to port 1.5, so that enable the buzzer. Okay, right, this way we can check the input bit. Then switch the register bank. How to switch the register bank? Okay, so problem is state the content of RAM location after following program. Okay, state the content of RAM location after the following program. Actually this is a program. What will happen after this program? Okay, so set B PSW 0.4, program status word 0.4. okay, set B, that means select the register bank 2. So program status word is actually this is a program. Okay, then move R0 comma 99, move R1 85, R2 3F, R7 63, R5 12. Okay, these are the immediate data that is loaded into the particular registers 1 2 0 1 2 7 and 5. Okay, right, this is a given program. What happened? State the content of RAM location after the following program. Okay, so what will happen here? PSW 0.4. okay, that is used for select bank 2. okay, here the solution is by default PSW 3 equal to 0 and PSW 0.4 equal to 0. Therefore the instruction set set B PSW 0.4 set, that means RS equal to 1 and RS RS1 equal to 1, RS 0 equal to 0. Therefore selecting the register bank 2. okay, register bank 2 uses a RAM location from 10H to 17H. After the execution of our program we will have the following. Okay, RAM location 10H has 99, 12H 3F, okay, then 15H 12, then 11H 85, 17H 63. Okay, actually each general purpose register R0, R1, R2 have some address. In that address the data are stored. So the general purpose register is behind the RAM. Okay, that is behind the RAM. So the R0, R1, R2 having the address, that address is stored in the RAM register. So here the register bank is, which register bank is selected? Second register bank is selected. So totally we are having the 4 register bank. So according to the program status word, we can change the register bank, okay, according to our program needs. Okay, so this way we can switch the register bank. Okay, right. Next one, so stack. Next we are going to see the stack, how to access a stack. Okay, see the example. Show the stack and stack pointer for following. Assume the default stack area. Okay, so default stack area. Actually, what will happen after the execution of this program? Initially, this is a stack position. Okay, just first we have to see the program. So move R6 25, R1 12, R4 F3. So before consider the alphabet, we must add 0 before the alphabet. Okay, F3. Then bush 6, bush 1, bush 4. 6, 1, 4 represent this register. These are these registers. Okay, this register is indicated by a number 6, 1, 4 like that. Okay, right. So we are moving the data, immediate data to the register. After that, we are push the particular register value into stack. Okay, so in solution, initially the stack is looking like this. Okay, the stack pointer point 07. Okay, 07. Okay, so after the execution of these instructions, bush 6, what will happen? The 25 is loaded into here. Now the stack pointer point 8. Okay, after that bush 1, so the 12 is loaded into next location. Now stack pointer point this this data 12 9. After that bush 4, so 4 means R4, R4 having F3, the F3 is moved to next location of the stack. Now the stack pointer point 0A. Okay, the stack pointer point 0A, that is a F3. Okay, so now the stack is filled by 3 data. The stack pointer current address is 0A. Next we are doing the pop operation. What will happen after the popping operation? Okay, pop 3. Okay, pop 3 means what will happen? Actually initially here in the stack, see, actually that program is different. That is bushing into stack, that is different. Okay, so every bush operation the stack value is stored in RAM. Okay, so the stack pointer point the current data, last pushed value. Okay, next we have to push the data, means we have to bush, that means pop means the first data is taken out. Okay, F3 is taken out, then 12 is taken out, and then 25, that is a first in first out, last in first out format. Okay, right, first in last out format. Next one is a popping of stack. So see the example. Examine the stack, how the content of the register and stack pointer after the execution of the following instructions. So pop 3 means R3, pop 5 means R5, pop 2 means R2. Okay, so initially before the execution, this is a stack position, stack pointer point 0B. Okay, after this pop 3 execution, the stack pointer address is decremented, so 0B to A. Now the 54 is loaded into R3. After the second execution, pop 5 means, so again the stack pointer is reduced A to 9, and the next data F9 is loaded into R5. Then pop 2 means what will happen? The stack pointer is again reduced, that is a 08. Okay, then the 76, this data the 76 is loaded into register R2. Okay, so this way we are popping the stack. So whenever we are pushing the stack, at the time stack pointer address is incremented. Whenever we are popping the stack, at the time stack pointer address is decremented. Okay, right. So but the stack pointer point the topmost data, top data. Okay, right. So this is the stack operations. Next one, you are going to see the loop operation. How to perform the loop? Okay, see the example. Write a program to clear accumulator, then add 3 to accumulator 10 times. So 10 times means we must consider the count value. Okay, right. So initially accumulator is cleared. After the clear, we have to add 3 in 10 times. Okay, what will happen? This program adds value 3 to accumulator 10 times. Okay, initially move a comma immediate data 0, so accumulator value is now 0, that is cleared. Then move r2 comma 10, this is r2 is considered for count value. Okay, count value that is moved to r2, that is a count is 10. Then add a comma 03, here we are consider one loop again is a variable that is considered considered in the instruction add a comma 03. Okay, then decrement jump no 0 r2 is a count value, that is decrement 1, that is 9, it will become 9 and it is not equal to 0. Okay, then we are continuing the loop again. So now the second time added, so initially the a equal to 03, after the second time the a 03 plus 03, that is a 6. Then again we are decrement and jump no 0 r2, so decrement then jump no 0 r2 again. So r2 is checked every time whether it is equal to 0 or not. If it is equal to 0, then the loop will break. If it is not equal to 0, then loop will continue again. Okay, right. When it is become 0, this loop will break. Then save the result in r5 is equal to r5. So move r5 comma a. So the result is present in a, that is moved to r5. Okay, so this way we can make a loop by using count value. So here the counter is any register, any general purpose register is as a counter. Okay, so we load the data into particular register, then we can use the counter. The condition is DJNZ, that is an important instruction. It performs the two operation. D means decrement, JNZ means jump no 0, whether the count value is 0 or not. It check the count value 0 or not. Okay, so that is a mainly used for loop purpose. Okay, then loop inside the loop, that is a nested loop. Okay, see, write a program to load the accumulator with the value 55 and complement the accumulator in 700 times. So 700 times. Okay, right. Since the 700 is larger than 255, the maximum capacity of the any register, so we can use 2 register to hold the account. The following code will show how to use R2 and R3 for count. So actually we can use the maximum data is 255, but here the count value is 700. So we have to use 2 loop. Okay, so one is 70, another one is 10. So 70 into 10, that is equal to 700. Okay, right. So the what will happen? So load the program, load the accumulator with value 55H and complement in 700 times. So initially we are loading move a comma 55H. Now a equal to 55H. After that we are moving the count value. First count is 10. Okay. Second count is 70. The first count is moved to R3 register. Second count is moved to R2 register. Okay. Right. So we are consider 2 loop next and again. Okay, so the CPLA, after that we are CPLA. First we are decrement the R2, that is a inner loop. Okay, now the inner loop is decremented, that is R2 is decremented. Then jump no 0 again. So this loop executed is in 70 times. Okay, 70 times. This loop is executed in 70 times. Okay, when the R2 becomes 0, at the time this instruction is executed, DJN is at R3. Now R3 is decremented by 1 and we are entered the next. Again we come to here, then this in complement 700 times, sorry, 70 times. Okay, then this instruction will execute. So this way, every time the complement is happen for 70 times. So totally 10 into 70, we can achieve 700 times of complement of given input. Okay, right? So the R2 is used for inner loop, R3 is used for outer loop. Okay, so in this program, R2 is used to keep the inner loop count in the instruction djnz R2 comma again. Whenever R2 becomes 0, it falls through the djnz R3 next is executed. This instruction forces the CPU to load R2 with a count 70 and the inner loop start again. This process will continue until R3 becomes 0, and when R3 becomes 0, the loop will break. Okay, so this is a nested loop inside another loop. Okay, right. Then conditional jump example. So write a program to determine if R5 contain the value 0. If so, put 55 in it. So R5 equal to 0, then put 55. Move a comma R5. Okay, move a comma R5, then jump no 0. Next, move R5 comma 55. Understand? So R5 value is moved to accumulator. Okay, and check the R5 value. Jump no 0. Next, jump if a is not equal to 0. Okay, not equal to 0 means it is jump to here. If it is 0 means it will execute move R5 equal to 55. Okay, if R5 is 0, then we are moving 55 to R5. Okay, this is a conditional jump instruction. If it is not equal to 0, this move R5 instruction, this instruction not executed, this will skip the next here, it can jump to here. Understand? So R5 equal to not equal to R5 not equal to 0 means 55 is not moved to R5. If R5 equal to 0 means 55 is moved to R5. Okay, right. This is another one, conditional jump instruction. So find the sum of the values 70, F5 and E2. Okay, put the sum in the register R0 lower byte and R5 higher byte. So we are having the three values. We are adding the sum and put the lower byte in R0 and higher byte in R5. Okay, right. How to do? First we are clear the accumulator. So accumulator equal to 0. Next, move R5 comma A. That means R5 is also clear. R5 is also 0. Then add A comma 79H. First data is added with A. Initially A equal to 0. So 0 plus 79. Okay, 79H. Next, jump no 0. JNC. No carry. Jump no carry. Add the next number. Okay. Add the jump no carry. Then we are jump to this loop. Okay. If it is carry means increment R5. Right. So jump no carry. Then n underscore 1. That is a loop. First loop. Okay. Carry is not present means you jump to here. Carry is present means execute INC R5. Okay. Suppose carry is not present means we execute this, add the second data. So A plus F5. So A equal to 79, F5 that is a 6E and carry equal to 1, CY equal to 1 here. Initially carry, no carry. Okay, 0 plus 79, there is no carry. Carry equal to 0. So that directly come to here. Then jump no carry, jump to this loop. If it is carry is present, so here INC R5 is executed. Okay, right. Next, the carry is present, so INC R5 is executed. After that, we are adding the next data. Okay, then jump no carry over. The program is over. The data is stored in R0 register. Okay, then okay, increment R5 and okay, then after adding the third data, the carry is generated. So again increment the R5. So now R5 value is 2. Okay, right. If CY equal to 1, increment R5. Okay, now R0 equal to 50H. So the sum value, okay, r5 equal to 0 2, that is a carry. The carry is 2, sum equal to 50, that is stored in r not register. Okay, right. So this is a conditional jump examined. Okay, so this way we can program in 8051 microcontroller. When compared to 8086, 8051 microcontroller is very easy to program. So we have a general purpose register, 8 general purpose register, so we can use that register for count and any other purpose. Similarly, we can having so many conditional instruction, so that is used to reduce the program size and increase the speed of the program. Okay, right. So this is a programming of 8051 microcontroller. Okay, thanks for watching. Thank you, students.